In this video, we're going to talk about how quantum mechanics and chemical bonding are related. And this is going to eventually lead us to something called molecular orbital theory. So if we look at an s, a p, and a d orbital and their three-dimensional representations, sometimes we'll shade each of these orbitals. And the question is, why do we shade these orbitals the way that we do? And what do the shapes really relate to? So the shape of an atomic orbital, which are shown above, corresponds to the probability of finding the electron in a certain location. And sometimes chemists refer to these as probability density functions. So where is this electron in this particular orbital most likely to be found? Okay, Heisenberg had his uncertainty principle, and he talked about how we don't know the exact location and momentum of a particular electron. And this is because our electrons act as waves and particles. So we have to keep both of these in mind. And Schrodinger came up with an equation that said H psi is equal to E psi. And this psi part right here is called a wave function. And this wave function is going to describe the path of the electron. And we can relate this to differential mathematics. When we solve this equation, there's something called a node. And a node is an intermediate point at which the probability function goes to 0. So there's a 0 probability of finding that electron at a particular node. And if we look back up to the p and the d orbitals, the nodal plane for the p orbital is right here. And the d orbitals for this particular d orbital are going to lie right along the axis. Okay? So when we look at nodes, there are two types of nodes that we have to look at. And those nodes are radial and angular. And we can look at the various probability density functions to determine our radial nodes. So if we look at the radial nodes of an s orbital, we can get something like this, where if we put the probability of finding the electron on the y-axis and the distance from the nucleus on the x-axis, for a 1s orbital, that probability function is going to look something like this. Okay, where there's a main probability of finding that electron fairly close to the nucleus. And there are no nodes here. For a 2s orbital, if we plot the probability versus the distance, we're going to see a graph that looks something like this. And at this point right here, we have a node. For a 3s orbital, if we plot the probability versus the distance, we're going to find that there's 2 nodes there. And the probability of finding that electron farther from the nucleus is going to increase as we increase n, or the principal quantum number. We also have angular nodes. And actually, if we wanted to look at a picture of this, before we get on to that, if we have our various s orbitals, the 1s, the 2s, and the 3s, these 2 radial nodes will correspond to these lines right here in the 3s orbital. So the 3s orbital, if we represent it over here on the right, will have 2 radial nodes. Another type of node is called an angular node. And the angular node is related to the azimuthal quantum number, which we abbreviate with an L. And we say that the azimuthal quantum number L for s, p, d, and f orbitals is 0, 1, 2, and 3 respectively. If we have an s orbital, it's completely spherical. There are 0 angular nodes. For a p orbital, we have 1 angular node. And for a d orbital, there are 2 angular nodes. And the number of angular nodes is going to be corresponding to the L quantum number, or the azimuthal quantum number. Okay? And all of these properties are related to the fact that the electron can act as a wave.